now. Okay, so for all practical purposes, it's impossible to achieve perfect shim in the brain. And these off resonances combined with an EPI readout result in pixel shifts. And to make things even more complicated, on top of that, you have dynamic field map changes caused by motion, respiration, or eddy currents. So it's fair to say that all DTI applications require some sort of distortion correction. And what one typically does is to treat the distortion corrections as a post-processing step. Specifically, FSL top-up method exploits the fact that the distortion depends on the phase encoding direction. By inverting the phase encode direction, regions that were stretched are now compressed. And from that information, you can calculate the distortion field and correct both images. So in practice, what you typically do is you acquire a blip up and down data set at the beginning of your acquisition, get the distortion map, and then apply it to the rest of your time series. But what most methods have in common is that they ignore the off resonances during the reconstruction and treat the distortion corrections as a post-processing step. In contrast to that, we suggest to make the off resonance correction an integral part of the image reconstruction, and we can do that by including an off resonance model in a hybrid space sense reconstruction method, which is a versatile algebraic reconstruction approach that can handle in-plane and multiband acceleration, phase inconsistencies, and arbitrary blip patterns. And we also suggest to acquire a blip up and down data set for each diffusion direction, and using existing toolboxes like FSL, we can estimate dynamic field maps. And then when we perform a joint reconstruction of the blip up and down data, that should result in off resonance and eddy current corrected images with reduced G-factor penalty. So how can we model the off resonances? So we start with a signal in 3D K-space, neglect off resonances along the readout direction. Because we have a Cartesian K-space, we can perform a one-dimensional Fourier transformation along the readout direction and bring the signal into a hybrid XKY-KZ space. And then we can write the signal at position xn as the sum over the unknown spin density weighted by the coil sensitivities and an arbitrary phase modulation. And the phase modulation now has two contributions. One is from the nominal gradient field, that is the K-space trajectory, and the other contribution is from phase due to the off-resonance field. We then write everything in matrix notation with the signal vector S, this unknown spin density M, and F is the effective encoding matrix, which is the Hadamard product of individual contributions like coil sensitivity variation. E encodes the nominal trajectory, and W describes off-resonance effects. So in order to solve for the unknown spin density, we use a singular value decomposition approach to calculate the pseudo-inverse F+, which we then multiply to the signal vector. We can further stabilize our solution by employing regularization, which within the SVD framework can be implemented straightforward by discarding eigenvalues below a certain threshold. And we then use the regularized pseudo-inverse to reconstruct our data. So here's an illustration of the effective encoding field. So we start with a signal in XKY space for a 2D example fully encoded, and we assume that we know the field map. So if we ignore off resonances, then F corresponds to the matrix notation of a one-dimensional Fourier transformation along Y. Inverting F reconstructs an image that has distortions. Now we start modeling the off resonances. Here's the profile along the red line. So the off resonance profile along the red line that leads to a linearly increasing phase over time. And that in combination with the nominal gradient encoding field leads to a distorted effective encoding field. And if we invert the distorted encoding field, then we correct for the distortions during the reconstruction. And that's the basic idea of the off-resonance correction approach in K-space. So all data that I'm going to show was acquired with a single refocus spin echo sequence with SMS and blip EPI support. And we acquired an interleaved blip up and down data set, one per diffusion direction. We were using FSL's top-up for the field map estimation, and the recon was performed offline in MATLAB. So the pipeline for the joint up and down reconstruction is the following. You start with your interleaved K-space data, perform a standard reconstruction that leads to a distorted up and down time series. Then you use FSL to calculate dynamic field maps that at that point include eddy current contributions. Then you perform the off-resonance correction on the up and down data separately, which hopefully gives you undistorted up and down data. And then you have to calculate phase difference maps between the two data sets that is caused by tiny head motion during the diffusion encoding. And then finally, you can perform the joint reconstruction simply by concatenating the encoding matrices from the up and down data set that forms a larger matrix that you then invert. So here's a slice from a high-resolution data set. Where's the video? Okay, now we see that there are quite a few distortions. And that's the same slice after correction with FSL. And the third video shows, again, the same slice, and it's the result of the off-resonance corrected hybrid space method. So what we can see here is that the correction in K-space works as well as the image domain approach. Up to now, that's not really an advantage over FSL, but it allows us to perform a joint up and down reconstruction. So for the previous data set with multiband 2 and in-plane factor 2 acceleration, a blip EPI sampling pattern looks something like that. And the resulting reconstruction here shown for a B-value B0 and B-value of 2000 has a certain G-factor penalty. And if we now choose the blip down samples to fall in between the blip up samples, we effectively reduce the acceleration factor, and the joint reconstruction has higher SNR, not only because of an averaging effect, but also because of the reduced G-factor penalty. Then that becomes even more obvious if we go for higher acceleration, 8-fold in that case, multiband factor 2. So the reconstruction has quite a few noisy regions at the center of the brain that correspond to increased G-factor penalty. And if we now look at the joint reconstruction, we can see that it has much higher SNR, and the G-factor penalty is reduced dramatically. So the same is true for FA maps generated from this data set. Here it even appears that the joint reconstruction can get rid of a false connection between the hemisphere that shows up in the blip up only data. So what do we make of all that? Of course, it's a downside that the acquisition takes twice as long because we have to acquire 2 TRs per volume to acquire the blip up and down data set. But that should be more than compensated by the higher scan efficiency because of the G-factor reduction and complex averaging instead of magnitude averaging. An additional benefit is that you don't have information loss due to signal pileup because you always acquire the corresponding encoding direction, and you get a direct and dynamic measurement of eddy current and off-resonance distortions. Potential next steps could be to combine the whole approach with optical motion correction and clean up dynamic field map changes, or acquire the blip up-down scan as a second spin echo that might speed up the method a little bit in terms of the acquisition time. And with that, I would like to thank you.
Mark.
I'll just shout. I guess I don't have to. Would it be meaningful to think about alternating the up and down directions for different diffusion encoding directions, so you don't actually have to do 2 TRs per encoding direction? That is, you could just take the interleaved directions and try and do that. It would be under the assumption that the field map is a relatively slowly varying function compared to the radial distribution of the diffusion directions, but it could save you this doubling the scan time problem.
I'm not. That sounds good, but you're reconstructing 2 different images then. If you have 2 different diffusion weightings, so I'm not sure if that's a good idea. But yeah, maybe I don't.
Yes.
Hi, thanks for your talk. So I had a question about some of the spatial smoothing that you might experience as a result of your method as opposed to the FSL method. Because one reason I don't use the field maps to correct for the distortions is because I'm afraid of applying some kind of smoothing to the data, which would then obscure where my signal is coming from. So is there an advantage to using your method to mitigate this problem?
Yeah, actually, I haven't thought about that until yesterday when I got the same question. So I do think that there might. I haven't looked into it, but I do think that it might be it might be advantageous to use the case-based approach, because you're not only shifting the slices around, but you also get the point spreads function smearing. You should get rid of that, or you should correct for that. So. But that's definitely an interesting thing to look at.
Yeah, okay, thank you.